In this lecture, we'll continue our exploration of exoplanets by talking about hot Jupiters and planet migration. The first signs of something very exciting going on was the properties of the very first exoplanet to be discovered. 51 Peg b was found by Michel Mayor and Didier Queloz, working at the University of Geneva in Switzerland. These researchers were not aiming to discover extrasolar planets or even study them. They were working on binary star systems, in particular the kind of binary stars that execute very tight orbits with orbital periods of hours or days or perhaps a few weeks. And so they were studying a series of stars, and in this case they thought they'd found a bust because there did not seem to be two distinct stars in this system. But when they analyzed the wobble detected in the Doppler shift of 51 Peg, they saw that it did have a companion, but in this case a substellar object, too small and too cool to be a fusion-burning star, but half the mass of Jupiter, so a giant planet nonetheless. And the most amazing thing about it was its orbit. It was a gas giant on an incredibly tight and rapid orbit, very close to its parent star, executing a full orbit in just over 4 days. Think of that. The orbit of Mercury, the innermost planet in the solar system, takes 3 months. And so this was orbiting dozens of times faster than Mercury. There is no analog to this first exoplanet in our solar system, where all the giant planets sit hundreds of times further away from their sun-like star. So this was not only a discovery that opened up the field of exoplanets, it raised a lot of questions. What was going on that a planet could exist so close to its parent star and so massive? The category of planets that they discovered with this first observation were called hot Jupiters, for the obvious reason that they are gas giants of order the mass of Jupiter, and they're extremely hot because they're so close to their parent star. The surfaces, of course, are buried under dense clouds for a Jupiter-like planet, but if you could calculate the equilibrium surface temperature, it would be 1,000 Kelvin or more, maybe 1,500 Kelvin for some of the hot Jupiters. And so these are all planets that are massive, they're gas giants, and they have very tight orbits. If not a few days, then maybe only a few weeks. After that first discovery, other exoplanets were found. And in the first batch of exoplanets back in the mid to late 1990s, a number of other hot Jupiters were located. Here are a few examples. And you can see that again, they're very close to their parent star, all much closer than 1 AU, which is the distance of the Earth from the Sun. And you'll see that in some cases, even more massive than Jupiter, 6 or 10 times the mass of Jupiter in the case of the lower two examples. This is about as massive as a planet can get before it starts to get to the boundary of being a star. Again, we have no planet this massive in our own solar system. Now, it was not surprising in one sense that such planets could be discovered. It's basically easier with any of the detection methods to find a massive planet than a less massive planet. So in that sense, the discovery of hot Jupiters was not a surprise, that they would be found first. But their existence was a surprise because it's not predicted by any theory of planet formation at the time. And so we can talk about what the theory of planet formation is and just see how unusual this is. And by the late 1990s, simulations were good enough to model the formation of a solar system with quite high precision. In all of those simulations, you could generate a solar system architecture like our own architecture, but in none of those simulations could you ever form a giant planet so close to its star. In other words, simulations suggested that such planets should not exist, or they could not have formed at the place we observe them now. So the discovery of hot Jupiters forced theorists and planetary astronomers of all kinds to reevaluate their knowledge of how planets actually form and what happens to them after they formed. The idea that the planets form at the positions we see them, for example in our solar system, and then stay there forever or for hundreds of millions or billions of years may be true, but it may also be wrong. Planets may actually move over long timescales or migrate. And the idea of migration is the key ingredient to understanding hot Jupiters. It also opens the box to a large number of possible effects in planetary systems where planets move around, change their position, fall into the parent star, sometimes are ejected, All of these possibilities make life very interesting in a planetary system. So this was an exciting time both for theorists who were trying to understand the phenomena and for observers who were trying to gather more information and understand if hot Jupiters was the normal situation or if it was an aberration that only applied to a small percentage of the exoplanet systems. The idea is that the gas giant planet is interacting with residual material in the disk. Not all the material is taken up by the formation of the planets, and the sun's starlight or radiation cannot drive away all the residual gas. That residual gas acts like a viscous force or drag, and so it can gradually change the orbit of a planet that forms further out. And so in simulations that included this information, or were precise enough to include this effect, it was seen that planets could indeed migrate from further out. In other words, they form further out, migrate inwards due to viscous forces in the very early phases of the planetary system's existence, and then they park on a stable orbit. Typically, they will park at a point where the gravity coupling with the star causes them to be tidally locked, which means one face of the planet is always facing the star, as Mercury is with the sun. So any planet on a very close orbit of its star will be tidally locked, and that locking of the orbit essentially stops it from falling all the way in. So a mechanism was proposed, and simulations supported this mechanism where migration was answering the question of hot Jupiters, explaining how they got to their final tight orbit. So the theory now is that the hot Jupiters form beyond the frost line in the same way that the giant planets are supposed to form, or that we imagine Jupiter and our solar system formed. But then due to interactions with debris, gas, or other planets in the disk, forces act to cause the orbital path to be altered. And with a strong enough interaction, the mass of the planet is sufficient that it will spiral in towards the star. Eventually, it's much closer to the star than where it formed. This model or idea addresses the fact that in the nebular theory, the star would evaporate the gases within the frost line, and there would be insufficient gas out of which a Jupiter-mass planet could form at a very close orbital situation. More recently, simulations have improved further. Computers are getting better according to Moore's law, basically doubling in their computational speed every year or 18 months. And so the most sophisticated simulations now show this behavior in detail. There's a theory that emerged in the 10 to 15 year ago time frame that's still held to be a legitimate theory of planet formation called the grand tack theory, which really discusses how planet migration may happen. It also discusses how Jupiter in our solar system may have changed its position early in the history of the formation of our planet system. And the motion of Jupiter, not always being in the same place that we see it now, could be responsible for aspects of the solar system that are interesting to us, such as the relatively small mass of Mars and the chaotic motion of many objects in the asteroid belt. Here we see the grand tack model, a simulation of the formation of our solar system. The circles represent the orbits of the giant planets, showing how they migrate inwards and then outwards. This is the inner part of the grand tack model, eccentricity versus distance from the sun. And you can see how the inward migration of the giant planets truncates the protoplanetary disk and leads to the formation of a very small Mars with very little material left of that orbit. This entire process takes less than 1 million years. Here's the outer part of the grand tack model. As the giant planets migrate to their current positions, they disperse the rest of the material in the outer solar system, prohibiting the formation of yet more giant planets. So the model is predicting chaos in some degree. There's regularity, of course, in the orbits of the planet once they form. But in the early formation phase, there's chaos, of course, because the planets build by accretion, and some of that accretion involves violent collisions, which can break apart objects that have just formed, as well as continuing to form them and make them more massive. The speculation of this model applied to our solar system suggests that the giant planets around us were affected by gravitational nudges or influences from nearby planetesimals. Remember, the planetesimals are the large rocky chunks that are of order hundreds to thousands of kilometers, so very small planet size or moon size. And the idea in this model, applied to our solar system, is that Jupiter and Saturn crossed what's called an orbital resonance, which is the ratio of their orbital periods being a whole number, in this case 2 to 1, making their orbits more elliptical. Anytime planets or moons undergo an orbital resonance, there's essentially a reinforcement of small gravitational nudges leading to a cumulative large effect. It's as if you had someone on a swing and you were pushing them on the swing. If you pushed them randomly or tried to push them randomly, you wouldn't increase their motion. But if you synchronize your pushing of the swing to be every time it comes near you, or every 2 times it comes near you, or every 3 times, you will increase the amplitude of the swing motion. It's the same idea with resonance in planet orbits. In this model, Uranus and Neptune also played a role. They cleared away some of the planetesimals, sending some into the inner solar system. And that's presumed to have caused the era of heavy bombardment, as it's called. In a standard model of the solar system, the debris is gradually cleared away, usurped into planets or scattered away, and diminishes over time. So we would expect the cratering history of any object where we can see its impacts over time to diminish with time steadily since formation. Instead, a puzzle had been known for several decades. Crater counts on Mars and the Moon seem to indicate a spike in the cratering history, or the number of impacts, about 500 million years after the solar system formed, so about 4 to 3.9 billion years ago. And this was a complete mystery at the time. Now, in light of these models, the explanation for that spike in the cratering rate is because of motions of the gas giant planets triggering a cascade of planetesimals, many of which were in the asteroid belt, into the inner solar system, where they, of course, could impact the Moon and, of course, the Earth, although that record has been lost due to erosion and volcanic activity. So this is a very neat idea, because this chaotic orbit idea, with added idea of resonances, starts to explain some very profound and basic features of our own solar system that have been mysterious up to that point. So now we have the idea that migration does occur in exoplanet systems quite generally, and it leads to the phenomenon of hot Jupiters. And the same phenomenon actually happened in our own solar system. So the current situation, the planets we observe in their current orbits, may bear very little resemblance to its original form. So our solar system does appear to be stable, long-term stable at the moment. But rewinding the clock, it's clear that things happen violently. Now, because of the chaotic nature of these phenomena, it's impossible to wind the clock backwards with absolute certainty. So we can no longer impute the initial conditions and play forward the history of our solar system. We can just say that it's likely that some of these chaotic effects happened, and we can point to some of the most likely ones. So the solar system now fits in the line of the view that planetary migration happens, and it may occur quite frequently and quite dramatically, not only in our solar system, but in others. Another feature that emerged from these simulations, which is interesting, is that the solar system, where the gaps between the planets are huge compared to the planets themselves, it appears that hypothetically you could add planets or have more planets with no effect. That turns out not to be true, because in computer simulations you can do the experiment. So the computer simulations have indeed suggested that the solar system is full in a dynamical sense, such that if you take our solar system in a computer and drop in another planet, say another Mars-like planet between the orbit of Mars and the Earth, or other planets elsewhere between the existing planets, and play it forward, the thing is unstable. Those planets are ejected, or planets move in their orbits or reach resonances and are chaotically disturbed. So our solar system is full in that dynamical sense. And the illusion of empty space we get from thinking of the spacing is not really reflecting what's going on in terms of the gravity of the planets. So chaotic solar systems is the way we have to think about solar systems. The other thing we've noticed, starting with the hot Jupiters, is that very few of these early systems look like our solar system. Now, we've already said that we have to be cautious in interpreting this because it takes a long time to find a full solar system with 8 planets. There are multiple planet systems that have been found, including a couple that have as many planets as our solar system. But we've only just been able to detect Earth-like planets. So we have not yet got enough data or enough sensitivity to find exact analogs of the solar system, and therefore have to be very cautious about saying they don't exist, or saying that they're rare compared to the hot Jupiter systems. This data is starting to become clearer, and people are starting to be able to make statistical arguments, but they do so cautiously because of our limitations of sensitivity. Either way, computer models clearly challenge earlier views that planets form an orderly way at their current locations. And we should be used to the idea that planets change positions, that chaos applies strongly in an early solar system and then episodically throughout its history. And this method, or this concept, has allowed us to mop up some interesting puzzles and questions about the history of our own solar system. So, to summarize this lecture, we've seen that planetary migration is a new ingredient of how planet systems operate. And it explains the puzzle of the very first exoplanet systems found, which were hot Jupiters, massive planets on very tight orbits of their stars, the like of which we simply don't see in our own solar system. The phenomenon of planet migration was not really predicted, but it can be explained now with computer simulations that show there's an element of chaos in the way planet orbits occur. And this chaos and the interactions between the early formed planets and the remaining material in the protoplanetary disk can cause interactions that send some planets occasionally completely out of the system and cause others to move their positions, and cause yet others to migrate to small orbital distances from their star and have the properties of hot Jupiters. And we think this behavior is normal. This is the routine for exoplanet systems. It's not special behavior. We've also seen that it applies to our own solar system in interesting ways.